Hey everyone, here is part 2 of the review sheet 1. We left off on problem number 6, finding the difference quotient. This is very similar to the last problem from the other video, except that it's a rational function to start. So the process doesn't change, it's just a little bit more algebra involved. It's easy to make careless mistakes on this, but that's really in the algebra part, not so much in understanding the difference quotient. So remember, our difference quotient is f of x plus h minus f of x, all of that over h. And so if we go ahead and substitute in, we end up with 1 over 2 times x plus h plus 5 minus 1 over 2x plus 5, all of that over h. Okay, so this is a complex fraction. I'm going to have to do a little maneuvering of things. The first thing I want to do is distribute here. So I end up with 1 over 2x plus 2h plus 5 minus 1 over 2x plus 5. All of that over h. Now don't fall into the trap. It's just a silly kind of careless mistake. Some people think, oh, well, I'll just multiply this by 2h over 2h so that I get a common denominator. You can't do that, right? This is all one denominator. This is all one denominator. So what I need to do is I need to multiply this fraction here, by 2x plus 5 over 2x plus 5, and then this one here by this denominator over this denominator. So when I do that, I end up with 2x plus 5. Remember, I'm trying to get a common denominator so that I can combine all of that into one fraction. So anyway, 2x plus 5 over 2x plus 5 times 2x plus 2h plus 5 minus 2x plus 2h plus 5 over that same denominator. 2x plus 5 or 2x plus 2h plus 5. And all of that is over h. So now I can combine the top into a single fraction. I end up with 2x plus 5, and then I'm just going to distribute that negative. So I end up with negative 2x minus 2h minus 5. All of that over this denominator, 2x plus 5 times 2x plus 2h plus 5. All of that over h. Now I do have some terms that cancel each other out, positive 2x, negative 2x, positive 5, and negative 5. Okay, so I'm left with negative 2h over that big long denominator, which is 2x plus 5 times 2x plus 2h plus 5. And if I divide that by h, that's the same as multiplying by 1 over h. And so now your h's will cancel. So you just have negative 2 over that big long denominator. I'm not going to write it out again, but it's over that whole denominator, this whole thing. Okay? So that's how you would go about doing a problem like that. Again, it's easy to make mistakes in there, so just be careful of your signs and everything like that. Okay, this next problem, number 7, should be relatively easy since we just pretty much did this unit. We have to expand this out, so we've got a couple of rules we have to go through here. We have the product rule, x plus 5 to the third plus ln of 2x minus 7. I'm rewriting this to the 1/2 power. Remember, the square root is just the 1/2 power. And then if I use my power rule, 3 ln of x plus 5 plus 1/2 ln of 2x minus 7, and that's all expanded out. In problem number 8, we're talking about population, and if you remember back in the last unit when we did that, we said population models compounding continuously. It's that same idea, and that's the formula we're going to use. If we have A as our population, and really the letters are arbitrary, right? But we have A sub 0 is our beginning population, of e to the kt, right? K is our growth constant, t is time, e is our irrational number, a sub 0 is our starting amount, or our starting population, and a is our ending population. So we have the two populations and the time. We first need to find k before we can figure out the second part. So we end up with 25,000 is equal to 15,000 e to the 10k. Right? If you divide both sides by 15,000, you end up with 25 over 15 on the side. And remember, we are taking the natural log of both sides, so we end up with ln of 25 over 15 is equal to 10k, and when you do that out, you end up with k is equal to 0.021459 something. I'm not going to write out the whole decimal. Okay? Oops. So now we have k, and now the second part says, assuming that the population is growing exponentially, how long does it take the population to increase by 40%? So we had to find that k value before we could figure out the time for this particular parameter of 40%. If we wanted to increase by 40%, that means we want to end up with the 100% that we had plus this new 40%, so 140%, right, which we can write as a decimal of 1.4 is equal to e to the kt, so 0.021459, whatever that is, times t. Okay, so first we had to find k, and now we're finding t, but I used the same process I did over here. I'm just taking ln of both sides, and with ln of 1.4 is equal to that 0.021459, whatever it is, times t. I'm just not writing out the whole decimal. And when you do that out, you end up with t is equal to 15.67 years. And you should use the whole decimal when you're doing this. You shouldn't really be rounding, and I think that some people did on the test. I didn't take off for that. You really should use the whole decimal and not round anything until you get to the end. I didn't take off if you did round the decimal, but it will affect your answer slightly, so make sure you don't round until you get to the end. Okay? Okay, problem number 9 is graphing a rational function. With the rational function, that's where we're dealing with asymptotes, vertical asymptotes, horizontal, possibly slant, those sorts of things. The first thing we want to do is figure out if we have symmetry, which we do because f of negative x is going to equal f of x. We get back the same thing we started with. So we do have y-axis symmetry. That'll help us when we're graphing it. Our y-intercept, that's when we find f of 0. If I just plug 0 in for x, I end up with 2/9. My x-intercept is where my numerator is 0. So if I set my numerator equal to 0 and solve it, I can factor 2 out, so I have x squared minus 1. And when you factor that, you get x is equal to plus or minus 1. Okay, so those will be my x-intercepts at plus 1 and minus 1. Now let's talk about asymptotes. Remember, we have vertical asymptotes wherever the denominator is 0. So x squared minus 9 is 0. That means that x is equal to plus or minus 3. Is where we will have our vertical asymptotes. And here we'll have those as well. And horizontal asymptotes, make sure you go back and look at the rules for this. But because my my degree of the numerator is the same as the degree of my denominator, I'm just taking my coefficient. So my horizontal asymptote is at y equals 2. Because I have a horizontal asymptote, I will not have a slant. And so from here, remember we said you plot points beyond and between your roots and your asymptotes. And so again, what I would do is I would go to the calculator and I would put this into the calculator and just use the points from there. It just saves you time and saves you from having to worry about making careless mistakes. May as well use the calculator to our advantage since we have it. Whoops, I think I forgot us x in there. X squared minus 9. Okay, and if you do a second graph, then you can just pull some points here. So let's go to some of the negative values here. So we've got at -5, we're up here at 3. At -4, we're up at 4.2, and here we're going down. So we get the idea of the shape here is going to be this. Remember, we know that we have y-axis symmetry, so I know that my graph is going to do the same thing over here. And I know that my y-intercept is at 2/9. Looks like my graph is going to end up doing this. And there you have it. You need to make sure that you show all of that work when you're doing that problem. Okay, real quick on these polynomial functions, and I'm going to give you a couple other problems in some other worksheets because it turns out that these don't have any x-intercepts, so you really have to go to the calculator to find all of your points. Really, the only thing that we can determine here is end behavior, right? When we look at this, it's a even degree, and because that leading coefficient is positive, I know the ends are up. I don't have symmetry because I have even and odd exponents. I know that my y-intercept is 4. And when I try to find my x-intercepts, when I use the rational root theorem, we talked about that in class, none of the synthetic division worked, which doesn't mean I don't have any roots necessarily. It just means that they're not rational, which means that they're decimals. And so I really don't have any way to do that other than to go to the calculator and look at that graph. So if I go to my calculator, let's see if I clear this out, and I put that function in, x to the 4th plus 2x squared. Oh, missed something. Minus 4x to the 3rd minus 4x to the 3rd plus 2x squared plus x plus 4. If you graph that, you'll see that's the kind of the general shape of it. And so then what I would do is just go to the table and plot some of those points. Obviously those are going to be kind of crazy, but plot some of the ones that you know and sketch out the graph. On your exam, I would give you ones that you would actually get some rational zeros that we can work through how to do that. So in problem number 10, both of those problems are the same in that they don't have any rational roots. So just go to the calculator and sketch out those graphs. Like I said, on the next review sheet, I'll give you a practice one that you can find the rational roots. Okay, that's it for this review sheet, everybody. We'll see you next time. Take care. Bye-bye.